Hello, for today's video lecture we're going to be talking about power screws. So a power screw, also sometimes called a lead screw, they're used to raise very heavy loads with a relatively small amount of torque. The trade-off is you have to twist these multiple times around and it raises the load very slowly. And friction plays a big role in how we analyze this, so this is why it's in the friction unit. So they can be thought of as really like a wedge or a ramp that is just wrapped around the pole. If you follow one thread, it goes up very gently and it's just going around and around and around. The nut is what's being slid up the ramp in this particular scenario. So rather than finding the kind of pushing force needed to lift a weight like we would do with a wedge, we're going to find the torque. Usually we spin the rod with some amount of torque and that'll raise the load up. So power screws at work, here are some kind of common applications. With something like this is a scissor jack right here. And so with this jack, you would use this handle to twist, and there's a screw in the middle and it pulls these two pieces together. So with just the amount of torque you're able to apply with your hands, you can lift something as heavy as a car with that. Even kind of bigger over here, we've got a jack that's designed to lift the kind of floorboards and big floor, just the entire house basically. So you kind of brace it there, you twist it right here with your hands, and you can lift up the entire house, or the floor of the house. So again, relatively small amounts of torque with very large loads. We're not going very far there, we're only lifting the car or the house maybe a couple inches. So if we imagine unwrapping the thread, the nut, we'd see the wedge kind of being represented this way. So we'd have the nut, which I'm going to represent as a triangle like this, going up a ramp. And so I've got some pushing force. This is what's twisting the nut around. Moving up the ramp, I'm going to have some load force. This is whatever I'm lifting. I'm going to have a normal force and a friction force as well, because I've got this contact here. So this is going to be the free body diagram, kind of the unwound state of my nut on this really long thread here. So one key aspect in this analysis is we need to find this lead angle, and the lead angle is simply, what's the angle from horizontal for my thread. So in this, I've got the thread, the nut, and the lead angle is again up from horizontal for that. So to find that, we're going to use kind of one of two numbers is what's commonly given to us. We're given the threads per inch, or kind of the pitch of these of the nut or the bolt. So with threads per inch, for every 1 inch we go up, we would go around. Say it's 12 threads per inch. We'd go around the screw 12 times to go up 1 inch if we follow that one thread. So that means for every 1 inch we go up, we're going to go around. So the circumference right here, pi times shaft diameter, times threads per inch, so like 12 times, would be that distance there. And so with got a right triangle, if I've got the length, the height, I can use the arctangent function to find my lead angle. The pitch is a little bit different. So for the pitch, we're just going around once. So this is just the circumference of my circle. And the pitch is the distance between two adjacent threads. And so that is the height of my triangle over here. And so the pitch would be the distance or the height over here. This is one circumference for the length. Again, I use the arctangent function to find my lead angle. So once I have this lead angle, I can go back and apply this to my free body diagram. So if we write out the equilibrium equations, we're going to want to relate this pushing force to the load force. Those are the kind of two inputs I have in my whole scenario. So these are my equilibrium equations. I do sum of forces in the x, sum of forces in the y. I'm not dealing with moments here. But in the x direction I've got the pushing force, a component of the normal force, and this right here is a component of the friction force. So I've replaced the friction force with mu k times the normal force. Alright, in the y direction I've got the load force, a component of the normal force, and a component of the friction force. Alright, so again, I don't really know the normal force, but if I kind of rearrange those equations, so I took both of those equations, I solved for the normal force, and I set them equal to one another, I can find a single equation that's going to relate the pushing force, which is kind of my input, that's what's lifting the load, to my load force, which is the weight I'm lifting up. And as we can see, this is dependent on the lead angle and that kinetic coefficient of friction between the bolt material and the nut material. Alright, we still need to kind of relate the pushing force though to something we actually use, so we don't actually just go around and push this bolt all the way around the thread. What we're going to do is hold that still and then twist the shaft kind of underneath of it. So when we do that, it's a simple kind of relating this pushing force I would exert on one part of the nut to actually the moment that I'm twisting this with. And a moment is simply a force times a distance. So this F would be my pushing force, this moment would be the torque I apply to the shaft, and this distance is simply going to be the radius of the shaft itself. Alright, so putting that back into my equation, I arrive at my kind of final equation. The torque I apply to my power screw is going to be related through this kind of large constant right here, depending on the lead angle and the kinetic coefficient of friction, times the load, times the radius of the shaft. And this is what we do to kind of relate those two features. Alright, so kind of moving on, changing directions, we're now going to talk about what's called a self-locking screw. So one thing that might happen, something after I'm applying a torque, I'm working with the car jack, I jack the car up, I let go of the jack, and then I want to go under there and replace the tire or do whatever I'm going to do to the car. So we're going to remove the torque from the scenario. And so I take that pushing force and it's now gone. I've got nothing on the shaft of the piece anymore. And in the absence of this torque, the friction force actually goes from fighting me pushing this up the ramp and it switches direction, and now it's going to be the only thing that is preventing this load from falling back down. So this is what's preventing, that friction force is what's preventing the whole thing from kind of unwinding and the nut from just lowering on its own. Alright, so if the friction force is not sufficient to prevent that from sliding from occurring, the load can lower itself on its own. And so if we look at something like our car jack or our house jack, if I wind this thing up and let it go, I want it to stay there. I don't want it to just kind of fall down on top of me, because if a car or a house falls on top of me, that's going to be quite dangerous. So if we want to make sure that that friction force in many scenarios is enough to make the screw self-locking, it's not going to lower on its own. Alright, so we can kind of use intuition. Generally, if we've got a really small lead angle, a gentle slope, it's not going to slide down. And generally, if a really steep slope, it's going to slide down the slope. So somewhere in between that extreme, there's kind of the decision point. Is it going to slide or is it not going to slide? So that dividing point between sliding down the slope and not sliding down the slope is going to be the self-locking angle. Alright, so any lead angles below this self-locking angle, the friction force is going to be able to prevent it from sliding. The load is not going to lower on its own. Anything above that, it will lower on its own, and that's not a self-locking system. Alright, so to find the self-locking angle, we're going to assume impending motion. So that means that I still have no pushing force, but the friction force is about to give out. So we rewrite that as mu static times the normal force. We're going to draw out the free body diagram like we have there. It's going to have an unknown angle. So right now it's not whatever lead angle we have. We are looking for theta locking, which is unknown. We're going to write out the equilibrium equations and kind of solve for that unknown angle, assuming impending motion there. Alright, so here are my two equilibrium equations. And in both of these, they look very similar to what I had before. Again, no pushing force, so it's a slightly modified equation. But the part that we want to find here is this angle theta. And so I'm actually going to use the top equation, the x equation only, to find that self-locking angle. Alright, so if I take this top equation, I'm going to move this Fn sine theta over there. Fn will cancel out on each side. I'm going to wind up with sine theta over cosine theta equals mu static. And the sine theta over cosine theta is just going to be tangent theta. And so if I solve for theta in that instant, the self-locking angle, theta locking, is going to be the arctangent or inverse tangent of the static coefficient of friction. And so again, if I'm above that, it's not self-locking. If I'm below that, I have a system that is stable. It's going to, the friction force is going to prevent it from unwinding on its own. Alright, so with that, that's all I have for screws. Thank you for watching, and I hope to see you again.